Well, good evening, ladies and gentlemen. You're very welcome to another meeting of the Heritage Society of Engineers Ireland. And on this occasion, I shouldn't actually be near the computer, because as soon as I lean on it, of course, the next slide comes up. But no harm. You know something about George Boole already. Members of the computer division, you're very welcome, and indeed any visitors, particularly the mathematics fraternity, to this event. Now, just to start, I have to just point out the emergency exits, which are the way you came in and the door on your right as you look at it, the right-hand corner. Also, if you switch off any mobile devices that you may have, just switch them off or on silent, we appreciate it. Now, the subject of our talk this evening, as you can see from the slide there, is the mathematician George Boole, and his bicentenary happens to fall on the 5th of next month, and of course he's best known for devising an algebraic system capable of describing logical statements that became known as Boolean algebra. This, of course, had a major influence on the development of digital electronics and software and internet searches, so a very important person in the mid-19th century. Our speaker, Owen Gill, is a chartered engineer himself and a lecturer in engineering at Waterford IT, and he has an interest, like myself, and indeed I hope a number of us, in historical aspects of engineering and historical figures from science and engineering, particularly those with an Irish connection. And in his talk, he'll tell the story of Boole's extraordinary life with a focus on his time in Ireland from about 1849 to 64. The development of his algebra and his book, The Laws of Thought, which, like all Victorian titles, had about two sentences following that, but The Laws of Thought is the short version of it, will be examined, and the introduction of Boolean algebra into computing and electronics will be traced. So I have much pleasure now in inviting Owen to give his talk, which he has entitled George Boole and the Laws of Thought, Tracing a Core Strand of the Information Age. Owen.
Thank you very much, Ron. Just to introduce myself, it's wonderful to see so many familiar faces and welcome some new faces here, and welcome whoever's out there in the digital world joining us on the webcast. My name is Owen Gill, and I am a lecturer in Waterford Institute of Technology, and I'm a member of the Agricultural and Food Division here and the Southeast region. So you're thinking Agriculture and Food Division, George Boole. I am neither a historian nor a mathematician, so I like to get my excuses early. As Ron said, I have a particular interest in the history of science, and I believe actually that you can't really understand engineering without knowing something about the history of engineering. Now, I don't really believe that statement. Well, I feel that that's true, and I would, being at the wrong end of such a kind of a dogmatic statement during the week, being upstaged in the concert hall, no less, after my introduction and being contradicted by the speaker then about the importance of mathematics. I think it's important not to make dogmatic statements, so I will say that I believe that understanding and appreciating the history of engineering helps us understand the profession of engineering. So, I run a centre in WIT called CalMast, which promotes STEM. And in 2006, we became concerned with we became aware that problems with mathematical preparedness for college was universal across Ireland, and we spoke to other people at the time, including uh, Morris O'Reilly was here, Siddhartha Sen from Trinity, Fiacre Cabra, and we decided to set up Maths Week Ireland, which I'm happy to say we have just finished celebrating our 10th Maths Week. So this is, we had over 250,000 people engage with mathematics around the island of Ireland, and we tried to make and draw on the rich stories and heritage of mathematics in doing that, in trying to excite people about mathematics, and indeed to show another aspect to mathematics, to put the story back in mathematics maybe that wasn't there certainly in my time in the textbook. Maths Week was enormously successful, and this is a postscript to Maths Week, an epilogue. And as Ron said, I am interested in historical figures. I'm probably more associated with Robert Boyle, differs only by one letter from Boole. I've also done talks on Callan, Da Vinci, and now Boole. And I found Boole, when I was aware of Boolean algebra, naturally enough, and that Boole worked in Cork when I was an undergraduate. But it's only since learning more about his life that I found what a fascinating character he is, what a remarkable contribution he's made to, I suppose, the modern world, and what a decent sort of a guy he was. And I'm very much indebted in this talk to this book and to Professor Des McHale, Boole's academic descendant in UCC, and this is the biography of Boole. And this talk, I'm going to talk about Boole's life and talk about the thought where he presented his ideas about the algebra of logic, and trace that particular strand down to the digital age. Now, Boole had, I suppose there's another strand you could trace through his probability into information theory, but we're only interested in tracing his algebra. He was born in 1815 in Lincoln, in England, and he died in 1864 in Cork, in Ireland, at a very young age. So this is basically, his life is inscribed between these 2 points, almost on the same latitude. It was fortuitous that Ireland offered him an opportunity that wouldn't have been, or possibly wouldn't have been forthcoming in England. So he's born in Lincoln, the great cathedral town, and he was the son of a cobbler. And much is made about Boole's humble origins, that he came from a very, very poor background and dragged himself up. And that gives the wrong impression, I feel. His father was a cobbler, which was a respectable tradesman. He was certainly orders below other mathematicians or scientists that we know from the age in terms of social status. But his father was an educated man. His father was, as say, a tradesman, running a business, having a shop. He wasn't an itinerant cobbler or something like that. And his father had a remarkable influence on his life, and without his father, presumably he wouldn't have amounted to what he did. His father taught him Latin. His father taught him mathematics. His father was, I suppose, he should have been a scientist himself, but of course that opportunity wasn't there for him. And he made his own telescopes, microscopes, that sort of thing. And he was involved in the Mechanics Institute in Lincoln. The Mechanics Institutes were organisations set up around England, and we had them in Ireland as well. And they were for the education and training of, I suppose, largely the working classes, but in science and engineering in particular. So there were places you could go. They had libraries, they had activities. So Boole had access to, I suppose we would say, informal education, which was to enable his formation. He was born in Lincoln. His first publication was in 1830. That was a poem written at the age of 14 in the Lincoln Herald, translated from the Greek, some obscure ode, and it was published in the local paper and caused a bit of a stir because irate people wrote in and said that wasn't done by a 14-year-old boy, rather like the sort of people who post comments nowadays below maths puzzles in online publications. So he was precocious and he was a prodigy. He spoke Latin, French, and German, and his father taught him Latin. And when his father felt Boole his son had outstripped him, he sent him to a tutor who was a local bookseller. And Boole then decided to teach himself Greek. So he borrowed Greek books and he taught himself Greek. And that's when he did this translation of a Greek ode, which, if we have time at the end, I can read you some of it. He went to various schools, and he ended up, after primary school, he was sent to Mr. Bainbridge's Commercial Academy in Lincoln. His father had many interests, and it seemed like cobbling wasn't one of his chief interests, and the business failed. And Boole had to leave school and immediately become a teacher. No such thing as teacher training in those days. He began teaching. He had several different posts, and his first post was with Mr. Hyam at his school in Doncaster, which was a Wesleyan school. And this is a fellow pupil, or a pupil at the time, who said he was asked to leave because he wasn't really following the Methodist tradition, and he was apparently caught doing maths in chapel. So another cause of his leaving at the end of 2 years was that he was so completely engulfed in his own studies so absent that the lads cheated him out of their lessons. He was a most excellent teacher when he had a pupil who could appreciate him, and he had one or two such at the time, but with the vast majority of boys who have no application and require drilling again and again in the same subject, he was the worst teacher I've ever met with. Instead of explaining, he lost his temper and set the pupil off in a pet, the lad too glad to escape the lesson altogether. They showed him each other's work, the same work several times over, and on their word that it was all right, he gladly passed it, to be again absorbed in his own book. This was always his failing. His brother William could not learn from him. He was so impatient if the pupil could not see the reason why as soon as he did. This was the second cause of his leaving. He was as highly respected as in every other respect as it was possible to anyone. So it seemed that as a late teenager, he wasn't the greatest teacher in the world, and he had little patience with those who couldn't grasp things as fast as he did. He moved on, and he opened his own school because it was more lucrative. He had to support his family, his 2 brothers, a sister, mother and father at this stage. So he opened his own school, and then one of Mr. Hall's academy where he had worked, Mr. Hall died, so he moved back there to take that over. It was a prosperous, established school. And then he moved back to Lincoln himself in 1840 and set up his own school in Lincoln, and had quite a following, reasonably successful. But obviously, as running your own school probably is a difficult business to be in. And also, running anything yourself, you would appreciate the demands on time. And this was a young man who was increasingly devoting his time to mathematics, and this was putting strains on his time. So he, in 1835, he was chosen to address the Mechanics Institute, and he wrote a long address about Isaac Newton, who of course was from Lincolnshire as well, so a local hero. And Boole's address is remarkable for a young man of 19, and to address the great and good of Lincoln society, and to be chosen shows how the city of Lincoln knew there was a genius in their midst. So his first mathematical publication came in 1841. In 1844, he wins the gold medal from the Royal Society, and apparently that was the first gold medal for mathematics. Although previously, about 10 years before, our own William Rowan Hamilton won the gold medal, but it was for a work of physics. So in 1844 he wins that, and that establishes him as gives him status as a mathematician, and a remarkable achievement for somebody running a school, supporting his family. And I think one of the other, apart from Boole's the exaggeration of his background, and exaggerating it, that he was the humility of his background, but the other one is that he is self-taught. Now, largely he is self-taught in terms of he didn't go to college. He left school at 16. He didn't go to college, but he was very lucky that there were people around, and that his father seemed to be well connected or respected in Lincoln. So Boole learned first from his father, so outside of school. The Latin tutor was a William Brooke, who was a bookseller in the town, which presumably, and had a lending library, so presumably that gave Boole access to books. He also had two other mentors, the Reverend Dixon and the Reverend Larkin. And the Reverend Dixon was loaning the 16-year-old Boyle Lacroix and Lagrange and Poisson, and Boole was reading these in the French, of course. I should say that mathematics in Britain had languished in the shadow of Newton for the previous 100 years, and it was only I think it was 1815 when Boole was born that that people like people like Babbage and that tried to rouse English mathematics from that, and to promote the mathematics of the continent, so particularly the French mathematics. And one of the people who was involved in that movement was Sir Edward French Bromhead. And Bromhead just happened to live just outside Lincoln. He was involved in the Mechanics Institute, and so he was another of Boole's mentors. And Bromhead was an FRS as well, a Fellow of the Royal Society. So very much so there was a connection with an establishment figure, in mathematics. He began corresponding with Duncan Gregory, who was the editor of the newly established Cambridge and Dublin Mathematical Journal, and he sent some work in there, and Gregory very much again mentored him, sent back revisions and advice, and started publishing Boole. So that was where he started publishing, and through that he formed, I suppose, relationships through correspondence with Cayley and De Morgan and William Thomson, who later Lord Kelvin. So he had a good network, and I suppose the world of mathematics, as maybe the world of engineering and wider science, but particularly mathematics, it's hard to ignore if if somebody can produce good mathematics, it's hard to ignore them. So I think in other areas, social ranks would have closed completely, but I think it would have been hard for people to ignore Boole's work, and certainly people like Gregory and Thompson, Cayley, these people in De Morgan were very supportive of him. So after you could say that from 1844 he was established as a mathematician. He did investigate going to Cambridge himself and taking a degree, but he wouldn't have been able to afford it, and maybe had he been single, maybe that might have been a possibility, but it wasn't a possibility. In 1847 he publishes the Mathematical Analysis of Logic, and this is where the Boolean algebra first appeared. The stimulus for this was a row that had erupted between Sir William Hamilton, not William Rowan Hamilton. This was William Hamilton, a Scottish philosopher who cared little for mathematics, but was a logician, and Augustus de Morgan, who was Boole's friend, and Hamilton had accused de Morgan of plagiarizing his work when de Morgan published on logic, and this gave Boole the impetus to work on logic. He says that about the age of 18, I think it was about the age of 18, back in Doncaster when he was teacher, before he had set up his own school, that he had a vision when walking across fields that you could express language in mathematics. So this was what Boole set out to do in the Laws of Thought. So in the first book was 1847, Mathematical Analysis of Logic. It was short, about 80 pages, I think, and he sets out his stall there and attempts to express logical statements in mathematical form, in algebraic form. Just to show how Boole had arrived, really. In 1848, the British government set up the colleges, and one of them was to be established in Cork, the others Galway and Belfast, and now UCC, of course. And there was a professorship in mathematics open for applications, and Boole applied for it. And you can imagine his CV was pretty short when it came to education, but he had the most wonderful set of references there. Five of the best known mathematicians of the day wrote glowing references for him, and he got the job. And in 1849 he moves to Cork. Boole is first professor of mathematics. There aren't very many students in the college. Boole is paid £250 a year for this, and that is a princely sum compared to what he was used to, and it also gives him time to work on his mathematics. And he would have been paid as well per student. The students would pay the professor. That, I believe, is going to be coming back again, that system. I think it was £2 in those days. It's probably gone up, or probably will when it is implemented, as many wish. So Boole hadn't many students, so that would have meant that he'd even more time to work on his mathematics. In 1854, he published the revised. It's far more than a revision of the Mathematical Analysis of Logic. It's a more substantial work called the Laws of Thought, and this is Boole's contribution to logic in this. In 1855, he marries Mary Everest. He knew Mary Everest since she was 18. He twice her age. She was the niece of a colleague, John Ryle, who was the professor of Greek and the vice president of the university. He had known her since he started, and finally, 5 years later, he married her. He overcame his, I suppose, any doubts about age gaps and social status, because there's quite a social gap between them. So he's established, he's married now in Cork, he's a professor, he has a steady job and income, and then in 1857 he's elected an FRS, a Fellow of the Royal Society. So by 1857 Boole has made it. 1859 he publishes a book on differential equations, 1860 finite differences, and so he's still very active, contributing. He's in the prime of his life, everything's established, and then in 1864 unfortunately he dies. So we'll come back to that. Just want to talk firstly about this is the quad, as more or less I think from Boole's days I think. He lived in 4 locations around Cork. Firstly, on the quays here, Grenville Place, and that's where he wrote the Laws of Thought. So one of the great pieces of the jigsaw that has become the digital age was produced at this site. He moved to Sunday's Well when he got married. He was in digs there. He moved to Sunday's Well. Then he moved out to Blackrock, and then into a very nice cottage in Ballintemple. So that's no interest really to us. I'll move on. Okay, so let's go back and the start of logic and look at the state of logic when Boole arrived. Why did he want to get involved? Why did he want to do this? So this is the School of Athens, and here is Aristotle and Plato. And Aristotle was the father of logic, and very much it was about categories and syllogisms. So if all the people in this room are engineers, that would be categorizing. So the people in this room and their engineers are, some of the people in this room are engineers. So that's sort of making categories. And then syllogisms was another form of logic. So here would be categories, and I'm just using something that's very simple and straightforward, so people can understand them readily. So if we were to say all Waterford people are Irish, now this doesn't have to be true. This is it's just one category. So all Waterford people are Irish, no Waterford people are Irish, some Irish people are from Waterford, and some Irish people are not from Waterford. So that's the sort of thing we can make in categories. So generalizing them, we have some A's are B's, no A's are B's, some A's are B's, and some A's are not B's. So this is pretty much what Aristotle was about, and for about 2,000 years afterwards, this is what the logicians did. And chief among them really were the monks of medieval times. And they were very interested in logical argument. It was very important for them to produce definitive proofs. Now, Aristotle produced a very nice system for being able to relate these. So some of these directly contradict. So all A's are B's is a direct contradiction of where we no A's are B's. These ones follow from it. Some A's are B's. That could be true. That's true if all A's are B's. A subset of it, and same over here. So this gives us a way of when it gets complicated, and it is a little bit complicated. It takes a little time when it's A's or B's. But if we were to plot our Waterford statements here, we can see what follows from what. So please don't accuse me of being provincial here, but I gave this talk firstly back in Engineering Week in Waterford, so I didn't see need to change it to Dublin. Okay, so that's now syllogisms are where we have two propositions and a conclusion deduced from them. So all A's are B's and all B's are C. And the conclusion is all A's are C. Not so easy to see there, but if we put in a practical example, which was all men are mortal, this is the famous one, Socrates is a man, so what can we conclude from that? Okay, Socrates is mortal. Okay, these things may or may not be true, but given these, this has to follow. So if we accept that, these have to follow. These may not be true. That's our logic won't establish that. So if these are true, that has to be true. So this is so it can get very complicated very quick. So does anyone want to have a go at this? If all knowns are truths and some unknowns are known, which of these statements must be true? All knowns are unknown, some truths are unknown, some knowns are not unknown. Okay, so it's not so simple all of a sudden. It can get just, it's difficult to process this sort of thing in our mind. But we can go and we can simplify, take a mathematical approach, and we can simplify it. So we have A's are B's and some C's are A's. So we rephrase it as that. So if some C's are A's and all A's are B's, then some C's are B's and then some B's are C's. So the answer is B, some truths are unknown. Okay, so that's just putting in to show that, you know, if we do Socrates is mortal and that, it can seem quite trivial, but this sort of stuff can get quite complicated. And why were the monks particularly interested in that? They weren't arguing over political activity or sporting results or whatever. They were arguing over theological matters and biblical matters. And they developed this system of, where they have figures and moods, and so any syllogism will fall into one of these categories, and from this they can tell you what has to be the conclusion. Okay, now these here, so A is of the form all A's are B's, so we see A here. This one here is one where we have all something or something, all something or something, and the conclusion will be all something or something. Now, you might notice these are all women's names, and this is how the monks remembered all of these, because they used to sing these. So all the monks in medieval were singing away about women in order to remind them of their logical studies. So in this case, we can use that system. It's of this form, and we know it's AII, which is A is all A's are B's and I is some A's are B's. So we can use this system then to find the conclusion, ZX, and it'll be some are truths. So it's just, I don't expect everyone to follow that exactly, or to be able to do the test at the end of this. But it's just to show you that this was quite sophisticated. It wasn't. They took it very, very seriously. So this is kind of the world into which Boole was coming. I'll just go back. So we can use another one here, and this is AII, because it's all is A, some is I, and the conclusion will be some as well, and it's Daria. Okay, so that's where Boole came in, and logic remained largely unchanged from the time of Aristotle to up to the 18th century. And there were problems. The people had this row between William Hamilton and De Morgan was over the quantification of the predicate, which simply means that when you say all Tramore people are from Waterford, are we saying all Tramore people are all Waterford people, or are we saying all Tramore people are some Waterford people? So they're two different cases, and the Aristotelian logic doesn't allow for that. So that's what Hamilton and De Morgan were trying to integrate into their treatment. So Boole wrote the mathematical analysis of logic rather quickly, and an essay towards a calculus of deductive reasoning. And as Ron said, in Victorian times, book titles ran to 2 or 3 sentences, much better than Boole's time or Boyle's time, where the skeptical chemist title runs to a full page. But so we're getting better as we move forward. Mathematical analysis of logic. I'll actually leave this till I go into the next one. He creates laws. He creates his laws for his algebra, and he's essentially creating a new algebra. He's creating his rules, and within that world, those rules apply. And if things go into that world from the real world, and we apply those rules, the conclusion has a validity in the real world. So that's more or less how he was working. And a lot of you here may be familiar with Boolean algebra, particularly people with electronics background or mathematicians, but electronic people would not recognize this as Boolean algebra, would you? It's so he has some very strange things and some things in it that mathematicians would have been horrified at the time. But this just shows he's actually using the Maclaurin expansion, right? Maclaurin's theorem from calculus to expand his own function here. And this is just there. That's his footnote here on this side, the Maclaurin's work, and this is Boole's work. So he's taken things from wherever he can to try and manipulate these symbols towards some sort of a conclusion, or to some sort of a meaningful conclusion. But in the intermediate form, there may not be any meaningful conclusion. It may have no meaning, he says. So it may have, but as long as you work towards find a conclusion that can be interpreted, then that must hold. So in 1854, he revises this and he improves it, and he publishes Laws of Thought. And this is the one that was written in Grenville Place in Cork. And he dedicates it to John Ryle, who is the vice president and professor of Greek, and who's the auntie of his wife, or who became the auntie of his wife the following year. Maybe he's trying to curry favour with his prospective uncle-in-law. These are the chapters in it, and essentially, so he talks about signs of the laws, he derives the laws, and he has methods of elimination and reduction and abbreviation. So methods of solving these equations and working towards some sort of useful conclusion. He treats logical propositions then and shows how to analyze them. He deals with the work of Clarke and Spinoza, two philosophers, and he gives an example of analysis. He then does a treatment of Aristotelian logic and shows how that can be processed with his algebra. Now then, from chapter 17 on, he talks about probability. So this up to here is your the source of the Boolean algebra. This is the treatment of Boolean algebra, and on its probability. And they are probably the two strands of the information age in itself, but we're going to confine ourselves to the Boolean algebra. So he starts with a proposition. He says that we can that the operations of language may be conducted by a system of signs composing of literal symbols, your x's and y's, operations such as plus, minus, and multiplication, and the sign of identity, the equal. We can make things equate to other things. And he says, these symbols of logic are in their use subject to definite laws, partly agreeing and partly differing from the laws of the corresponding symbols in the science of algebra. So there we might talk about the algebra of numbers. So that's your standard algebra, inherited from the Islamic mathematicians through Fibonacci into Europe, and it was, I mean, that produced its own problems with people thinking that the square root of -1 didn't have a meaning, which was thrown up by algebra. But he's saying that his algebra partly agrees and partly differs from this normal algebra. And this, he wasn't the first to do it. In 1843, William Rowan Hamilton in Dublin, on the same island, came up with the algebra of quaternions, where he decided to make up his own rules as well. So there was a precedent. Boole wasn't the one making a huge attack on the sanctity of algebra. There was a precedent, but Boole's algebra is different. So it's interesting that he sets out to try and look for ways in which the algebra of numbers can be used in his algebra, and some areas that it's just different. So he says if x stands for, on its own stands for white things and y for sheep, then we can express xy as representing white sheep. So we put them together, xy is white sheep. So what we would say in language is we would say things that are white and are sheep. So we would say something that's x and y, that's in category x and category y. Now, obviously this is the same as things that are sheep and that are white. So this is one of his early rules. So this is actually, I suppose, where Boolean algebra, one of the ways in which it confuses students, in that we're saying and this is in normal algebra, this is multiply. So we would say it represents the idea of something belonging to one category and another. Now, here he's saying in a case of y is equal to x, he comes up with this here. So he's saying that two literal symbols in the form xy expresses the whole of that class of objects to which the names or qualities represented by x and y are together applicable. It follows if the two symbols, so if they have exactly the same signification, their combination expresses no more than one on their own. So we're saying all things that are white and all things that are white is the same as all things that are white. So if x and y are the same, we end up with this. So it's seemingly innocent. X is equal to x. And that has, when we translate it into I suppose spoken logic, things that are in category x and in category x, well, they're just the same as things that are in category x. So x by x is equal to x, but that leads to something a bit scary. X squared is equal to x. So this is he lists it as a second general law. Now, x squared is equal to x has two solutions. It is when x is what? 0 and 1, very conveniently. So Boole then takes, Boole sees his x squared is equal to x is one of his general laws, and he notices that this, when you is valid for x is equal to 1 or 0. So it's not in there yet. So he says that these are the only numerical values which this logic can be equated with. So it can only, so the output of these can only be 1 or 0. And this in logical terms is something can be true or false. And we will see in electronics, it can be something that's either on or off. So our output is 1s or 0s. So so he's just going through various laws. He's trying to find parallel laws to the laws of algebra to classify his logic. So he then moves on to, I'll just show you his Aristotelian logic. So this is he puts it here we are, x's and y's. I think I used a's and b's earlier. So this is how he expresses this. So all y's are x's. So the category of y is equal to, this is not seen in Boolean algebra today. This v it means sum of x. So y's, all of y's are sum of x's. So x's, all y's are x's, but they may be part of x's or there may be other x's. So if we were to say all Waterford people are Irish, so the set of Waterford people is sum of the set of Irish people. So this v appears throughout, and it's a little strange at first. So he expresses the four categories of Aristotle, and then he lists four more, and then he expresses them there. Now you can see here this figure here, not y. That is simply 1 minus y. So 1 representing the whole, minus y, it's the whole without the y, so we would say nowadays not y, all things that are not y, and that's how he expressed it in his algebra. Now, so this is where he says, now the symbols of number, there are but two, these 0 and 1, which are subject to the same formal law, and there's no other roots than 0 or 1. Hence, instead of determining the measure of formal agreement of the symbols of logic with those of number generally, is more immediately suggested to us to compare them with symbols of quantity, admitting only of the values 1. So it's an interesting way to if you read the book, it's interesting to see the mind of the mathematician and how he's working. You know, it may strike people as kind of quite arbitrary when he decides we just have 0 and 1, but he's all the time relating to how these things can be interpreted in, let's call it, the real world outside his algebra. So it's very interesting. It's not something completely derived from first principles. He's all the time jumping out of his algebra into the real world. I don't like using that phrase, but that's what I mean. So he says we can only have 1s or 0s. We can't have any other portions. So here's an example, and again, Boole did not create this algebra in order to create the digital age. He did not. That was a long time afterwards. His motivation was, firstly, he had this at an early age, this desire that he thought that logical arguments or language could be expressed mathematically, but his very definite overriding motivation was that he felt it could be used to clarify biblical passages. Okay, so here we have, he mentions, he says, let us resume the definition of clean beasts employed in the previous example. Beasts are those which both divide the hoof and chew the cud. And suppose it required to determine the relation in which beasts chewing the cud stand to clean beasts, and beasts dividing the hoof. So this is obviously biblical stuff about beasts you can eat and beasts you can't. And Boole wants to know how we can relate how beasts chewing the cud stand to clean beasts. So he starts expressing it, he expresses it in his logic, and then he goes to solve it. And I'm not going to go through all of it. I don't think it's of much interest to any of us, the actual nuts and bolts of this, but I just wanted to show you the sort of thing he used to come out with. And again, if x squared is equal to x wasn't bad enough, here he has 1 divided by 0 and 0 divided by 0. Now this is the sort of, we're in the territory of kind of throwing the copybook back at the boy and telling him to leave the class. But again, Boole comes up with these I suppose very untidy expressions, but again he's pragmatic. He says that basically he looks at how these can be interpreted and he works backwards. So he allows 0 over 0 but dismisses 1 over 0 and 0 times 1 minus x by y. That's false, so that's gone. This is just, he says it has no logical interpretation, so we conveniently ignore it. And his conclusion then is beasts which chew the cud consists of all clean beasts which also divide the hoof, clean beasts which divide the hoof, x and y, together with an indefinite remainder. So 0 over 0 now is an indefinite remainder. Some, all, or maybe nothing of the unclean beasts which do not divide the hoof. Now, if you learn nothing tonight whatsoever, at least you've learned this. And you can go and apply that to your diets. Okay, so it just shows though that is very much different to what we would know as Boolean algebra today. Now, just to show, the truth table is a method of evaluating Boolean expressions. So instead of going through a lot of algebraic manipulation with Boole's rules, you can put in values, because we can only have values 1 and 0 going in. So let's put in all the different values and we can see what comes out. And this is known as a truth table, and it is attributed to Wittgenstein, the philosopher, who got involved in mathematics with Bertrand Russell, and then dropped it and went on to bigger questions in philosophy. But this is very much a truth table. I mean, that's in the laws of thought, but he doesn't pursue that. And it probably as well, I think I said before, so things we had 1 minus x, that's not x. So we would do not x as an x with a bar across it, in the electronics tradition. And Boole at one stage in the book starts using that, and I'd imagine it was just he got tired of writing it. He saw it as a simpler way, but he doesn't do it uniformly, so he does introduce it. Now, Boole unfortunately went to work one day and got very, very wet, and as a result he got into college, he lectured all day in wet clothes, and he walked home, and he contracted pneumonia. There's much, I suppose, speculation about what exactly happened when he got home. His wife, Mary Boole, was a follower of homeopathy, and one could be excused in those days for following homeopathy because germ theory hadn't been developed, and it was as good as, in fact, probably safer than the traditional medicine. And the story is related to by one of his daughters, is that he was wrapped in wet sheets, because the theory of homeopathy, that a little bit of what makes you sick will make you better. And supposedly he was wrapped in wet sheets, and some other accounts talk about iced water and everything dousing him and all that. But anyway, sadly, he died of pneumonia at the age of 49. He's buried in Cork. St. Michael's Church is a very nice little church, Church of Ireland, and a nice little graveyard. And if you are in Blackrock, it is nice to pop in. He was, I didn't say anything about his religious beliefs, but from what I said about his scriptural analysis, you can take it that he was a devout Christian. However, he had Unitarian leanings. He didn't believe in the Trinity, and but he did attend Church of Ireland, and as the established church, it would have been considered, I suppose, quite normal. But he also attended meetings of the Unitarian Church in Cork. He was, by all accounts, he seemed to be a very decent fella, charitable, unassuming to an extent, but he did engage in a number of rows, I suppose, took sides in academic rows, kind of a part of the job. It's unavoidable, but he seemed to be a very decent guy. He was very fond of his children, very kind to other people's children, and it was sad that the children were all left fatherless at a very, very young age. His very, very simple gravestone: George Boole, died December the 8th, 1864. Very, very modest memorial to somebody who had played such an important role in the development of technology. And this is where we go on to how was his logic applied. And it wasn't until the 8th century, and there was a certain amount of happy coincidence here. Claude Shannon was a student in the University of Michigan, and he was taking a degree in engineering and taking a degree in mathematics. So engineering schools, I'm sure, wouldn't have dreamt of putting Boolean logic anywhere near their students. What use was it? It was just esoteric stuff. But Claude Shannon was doing mathematics as well, so he was exposed to this, what was considered pure mathematics at the time, even though it has a great application, and even Boole himself felt that it was to be applied. But it was a very important early development in pure mathematics. So Claude Shannon, when he went along to MIT to do his master's degree, he was looking at relays, switches for telephone systems, that sort of thing. He was looking at that, and the thought came to me, remember this stuff he did in one of his other classes, and he had the great insight that Boolean algebra could maybe describe the circuits that he was working with, because these circuits had two states, 1 and 0. The switch was on or it was off. And he wrote this up in his master's, and it must be the most remarkable master's ever written. You can see here it is typed up. You can access it online. 1936, and I'm not sure if he would be allowed, it would be thrown back at him these days. It's only 80 pages long, and I think he has only about 5 references in it. And these are his drawings. Look at them. Shocking. So this 80 pages or thereabouts is where Boolean logic was applied to electronics, and this is the start of the modern digital electronics as we know it. So he has a number of conditions here of relays. There's just one relay. So a relay is essentially a switch. Okay, so this represents a wire coming in carrying electricity, a wire going out, and if we close the switch across it, the electricity will pass from A to B. we leave it open, there's nothing there. So we would immediately think if there's nothing there, it's open, it's 0, because there's no current. And we would think if it's closed, then it's a 1. What we have here is 2 in series. So if they're both closed, then the electricity goes off past it. And here we have 2 in parallel. Now, there's just one complication with Shannon's work, that he considered when a switch was open to be a 1, which is kind of counterintuitive to us. Well, I mean, it's not obvious to us. So he considered if that was open, that was a 1. So if that was open and that was open, so this becomes x. I didn't really go into the use of plus. I said about x multiplied by y being x and y. If something is either x or y, we use a plus sign, and it follows similar rules to addition in normal algebra or arithmetic. So this here in Shannon's work is an OR gate. It does a function of it does a Boolean function of x or y. So if that's open or that's open. And this one here is an AND gate. But if we don't take that approach, the Shannon's approach, and this is where it is confusing just here. If we take it that this switch is closed, and this if we take, so we're actually running the opposite way. We would consider if this switch is closed that this will be a 1. If that's closed and that's closed, that this will be a 1. So this no longer will be an x or y. This then, if we reverse our interpretation of this, this becomes what we call an AND gate. So it only works if that and that are closed. And the same here. So I'm going to demonstrate that. Sorry, that is confusing. It's not my fault. It's Claude Shannon's fault. That was his approach. But this is a very remarkable document, and if you are interested in Boolean logic or in anything to do with electronics or computing and that, it's well worth reading. It is remarkable that somebody so young made that profound connection. And he says in his, this is his, he says, we are now in a position that the algebra of logic, originated by George Boole, is a symbolic method of investigating logical relationships. The symbols of Boolean algebra admit of 2 logical interpretations. If interpreted in terms of classes, the variables are not limited to the 2 possible values 0 and 1. This interpretation is known as the algebra of classes. If, however, the terms are taken to represent propositions, which is what we were doing earlier, the calculus of propositions, they're limited to 0 and 1. So he is saying that there is this pre-existing mathematics that applies here. And you can see there he uses up I think 3 of his 5 references in that line there. So he talks about it being the hindrance, so the open contact. So if the relay is open, it says x is equal to 1. If the relay is closed, then x is equal to 0. And he lists then the rules of Boolean algebra. And these are, Boole doesn't list them in a table. We find them everywhere else since in modern textbooks. They're all listed as a table similar to this. And then at the end we have De Morgan's theorem. And De Morgan's theorem helps you translate if you have something that if not A's or not B's, it can translate them into AND statements. Okay, so and that was Boole's friend De Morgan. And using this, we can convert. We can show that Shannon's statements are the equivalent of our modern AND and OR gates. So this is how we would see them now. We would see if there's a dot or if it's just AA, that is an AND, and if it's a plus sign, that means OR. So that's a way that does confuse students, where we see a plus it's an or, and when we see a multiply, it's an and. But what we're saying is, in this case, we would be saying, well, here, we would just, if we were saying a and 1 here, sorry, this is a and 1 is equal to a. So if something is class A and it's everything, then the resulting class is A. And so if it's a member of class A and it's a member of the universe, then it's A. And then this is the OR. So I'll show you some examples. Sorry. I'm going to show you how this is implemented in real in logic gates, okay, in electronics. Now, I'm sorry, it's difficult to explain this without actually. It's easier to write it on the board and work through it. So the last few minutes may not have made all that much sense to some people. So let me just show you two of the basic logic gates, and I'll show, and we can see maybe how his logic actually works and can be used then to. So I have here. Now I have some very crude and purposely crude devices because I didn't want to use transistors or a silicon chip or something where you wouldn't be able to see anything. So everyone is familiar with light switches, and that's what we have here. So in this case, the power would run through this switch and this switch, and we have a little light here. These two lights indicate whether these switches are on or off. Okay, and hopefully. Okay, so we switch the first switch on, and we have our light goes on here to indicate that the first switch is on, but the light doesn't go on now. However, if we turn the other switch on, the other switch is on, but our output isn't on. But if we have both of them on, our output is on. Okay, so this means, and it might be obvious to a lot of you, that if the electricity has to flow through both of them, both switches must be closed for the electricity to get here. And this is a lot of your domestic lights at home will be wired just like this. Okay. Actually, a little bit more sophisticated, but you may have it like this. In this case, if we look at it, we have, if this is 0 and this is 0, if we call this, if the switch is off, we call it 0. This switch is off. So this is 0 and this is 0. The output is 0. If this is 1 and this is 0, the output is 0. If this is 0 and this is 1, the output is 0. And the output is only 1 if this is 1 and this is 1. So this is an AND gate. So it has to be, if we call this one A and this B, A and B must be on for the output to be on. Okay, so that's an AND gate. And it may seem quite trivial, and in many ways it is. It's not trivial, but it is at least simple. Now, here is another configuration, and in this case we have the electricity can run up here onto this switch, up here onto this switch, come together and to that switch. So in this case, if we switch that on, we have an output. If we switch that on, we have an output. And if we I have something loose here now. Yeah. Okay, so so this is known as an OR gate. One or the other or both. If one or the other or both are on, then this is on. Okay, so that's an OR gate. So they're two of the basic logic gates. and it's running on Boolean algebra, and we can write down those simple statements, and we can say input 0 and 0 gives 0, input 0 and 1 gives 1, input 1 and 0 gives 1, and input 1 and 1 gives 1. And they're the two basic gates. We can also have a NOT gate, which just negates what, if it's a 1 going in, it'll be a 0 going out. If it's a 0 going in, it'll be a 1 going out. So in other words, if it's off, it'll go on. If it's on, it'll go off. And with those three gates, you can build anything. Okay, now, so with those three gates, and that is what Claude Shannon showed with his relays. And they are just the three building blocks of computers. Okay? They're the brains of a computer can do everything with just those gates. And it requires Boole's algebra to operate them. Okay, so that's very important. But the electronic engineer must use Boolean algebra to simplify these sort of circuits, as Shannon first did. So you use those laws of Boolean algebra that have been extracted from, or descended and refined from Boole's first expressions in the laws of thought, and you use those to simplify very, very complicated circuits. So if we had load more switches there, we might find actually that we could do, maybe with a circuit that's had 10 switches in it, we might, by using these rules, we might find that we could do the same job with 5 or whatever. And that obviously is very important when it comes to things like, sure, I had one here somewhere. Yes, there we are. Your mobile phone, which has hundreds of millions of those logic gates in it. So, so taking Boolean algebra and with the Shannon's relays, we were, I suppose, on the cusp of the digital age. It just required for the transistor to be invented not long afterwards. And a transistor in this context is a switch. So we can use a transistor to do the job of that light switch. Obviously, making a computer with 100 million of these will be a little bit cumbersome, and will get very hot very quickly. But when the transistor came, the transistor works as a switch, and then we had the last 50 years, we've been able to make tinier and tinier transistors, and we're able to put those transistors onto wafers of silicon and fit hundreds of millions. In fact, the new iPhone, I think, has 1 billion transistors inside it. So, and indeed, when I say we, I mean it in the same manner as we won that match. I had nothing to do with it. I do not make these. But I have, I have amazing admiration for people who do, and I think it's great to have a certain appreciation, at the level that I do in these things, because not only can we be in awe and respect of nature and natural things, but also in awe of the great achievements both of mathematicians and engineers. Now I'm going to just quickly say something about Boole's legacy. I'm sorry I'm going well over time here. This is Boole's 200th anniversary, and University College Cork is honouring him with a program of different events. And there has been a television program broadcast on RTE. It wasn't available on the playback or whatever, the real RTE player, but I think it will be, if not now, it will be soon, because they're holding off, I think, to have private showings of it. Interestingly, Boole had sided with Ryle, who had terrible rows with the president of Cork, of Queen's College Cork, Sir Robert Kane, who was an FRS and a distinguished scientist himself, but Boole found himself on opposite sides with Kane. It should be welcome, therefore, that the present president of Cork, Professor Murphy, features so much in this documentary, as does our old friend Des McHale, who has been, I would say, single-handedly championing the cause of Boole in UCC, and he is commemorated in this plaque, for instance, over the house in which he wrote the Laws of Thought. So the house, the book that we're arguing tonight, has changed the world. Here is a nice evening view of it. Unfortunately, if the sun shines on it, we see it's derelict. It's a very unhappy state. And while there are plans afoot by Cork City Council and in association with UCC to renovate this and restore it and put it, it will be, I think, accommodation for academics, which is which is a very nice idea. People following in the footsteps of Boole. However, it's hard to know how such a building could be allowed to reach this state. And I think I feel I have to comment on it. I have to wonder. Lots of you know this building here. It is probably the largest centre for microelectronics research, a huge internationally respected I suppose the jewel of UCC's research, and it's very sad that the people of Cork let this building rot. Thankfully, anyway, that will be changed now, and it will be up and functioning for visiting academics. I should say about his biological legacy. He had 5 daughters, each of which were remarkable. Mary married a mathematician, Charles Howard Hinton. Margaret married an artist. Alicia made important contributions to 4-dimensional geometry, and she was, I suppose, the nearest in that regard to her father. And she was self-taught, because you can see that she was only 3 or 4 when he died, so he didn't train her or anything. She made these models representing 4-dimensional geometrical shapes herself. Didn't go anywhere with them, and years later somebody else, another mathematician, had published on it, and she saw it, made contact, and made important contributions. So remarkable, not just as a woman at the time contributing to mathematics, but as a self-taught woman. Lucy was the first female professor of chemistry in England, another person who broke new ground. And Ethel was probably the most remarkable or famous of them. She married Wilfrid Michael Vonage, who was a revolutionary and a scientist, and she wrote the novel The Gadfly, which was one of the greatest selling novels at the turn of the 20th century. We've done our own little bit to try and celebrate Boole this year. In Maths Week, we produced these posters about Boole, showing how his contribution to the digital age, and trying to show young people the various ways in which they owe to Boole the devices that occupy most of their waking hours. And so these posters went to every school in Ireland, so hopefully they're hanging in all schools north and south, and getting young people curious to know who was that guy, and what did he do, and why should and maybe some of these would go off and research. Some of them might be inspired to become mathematicians, but at least, hopefully, they will have a greater appreciation of mathematics and a greater appreciation of what we owe in our lives to mathematicians and engineers. So with that, I'll finish. Just to say, sorry, I was anxious when I was talking to Con, the chairman of the Heritage Society here, that I would be able to do something before November. So that's why we picked tonight. And because the 2nd of November is his 200th birthday. And if anyone is involved with schools at that, the UCC have developed a program called Boole to School, and they have, I think at this stage, about 25,000 young people signed up to do special Boolean activity on the 2nd of November right around the world. So anyone who might be interested in that, please pass the message on. So with that, I thank you for your patience and your attention, and I invite questions or comments or discussions from you all. Thank you. Okay, well in that case you can come up to me afterwards if there's anything pressing. Or, and I would, once again, another plug, if you want to know more about Boole, this is the authoritative text, Des MacHale, who, as I say, we owe a great debt to for keeping Boole's memory alive in the intervening years between his centenaries.
Well, I think by your applause, I no need to thank Owen for his presentation. I was a little bit nervous about coming tonight, but because I searched on Wikipedia and there was a first lessons in Boolean algebra. I didn't get beyond line 1. I did classical logic in college, but not mathematical logic, so this was all rather new to me. But I must say that Owen presented it in such a way that I think we've all learned something. Even the mathematicians amongst us have been reminded of the debt we owe George Boole with his Boolean algebra, and of course the digital age that followed. I was reminded at one stage that some Waterford people are wits and some are not, because Owen, I think, is from Wits, isn't that right?
That's right.
So would you say that some Waterford people are wits and some are not, or?
Well, would that be wits with a capital W or a small W?
What I was rather surprised by was in the, I didn't follow the development of the Boolean algebra in detail, but at one stage there was in brackets or a comment beside it which said, known cases of failure accepted. What does that mean? In other words, it's not exactly what you see, but it doesn't cover all cases.
It works except when it doesn't work.
Exactly. Right. Well, are there any other comments from the floor? Yes, sir.
First of all,
No.
thanks for a marvellous talk about great breadth. Just to point out that as well the wonderful work that's been done in UCC. We were fortunate to be there at the end of August for 2 about a dozen conferences that were held late August and September. And they've really done a terrific job there.
just to reply to some of that, the Mary Boole, I would say, I mean, there is a letter quoted in Mackayle's book from, or a passage from a daughter to one of the other daughters, referring to this about the wet sheets. However, he didn't fare the worst of the Irish scientists. John Tyndall was fed poison by his wife in mistake for medicine, and we can't condemn her for that. And I mean, Mary Boole and George Boole seem to be devoted to each other. They're very happy. She was an extraordinary woman, and I'm glad that Des is going to turn his formidable powers to looking at her role. However, there are he has some very interesting quotes from her, which some of which she was very much an extraordinary and independent thinker, but some of the stuff that he relates shows her to be a bit of a crackpot in other areas. But then it takes people like that to do, to certainly to bring up 5 daughters to have such extraordinary careers. In terms of Hamilton, it doesn't seem clear why Hamilton didn't engage with Boole. It's supposition to say that it was because of class distinction. It may well have been other aspects that, like the fact that maybe there was, I don't know, there might have been a resentment to this upstart university. There are amazing, there's amazing comparisons and contrasts in their lives. There's so many parallels. One is that both of them were appointed professor without a degree, although in Hamilton's case, just before his, just when he was before his final exams. But they were child prodigies, languages. There's so many parallels. Hamilton definitely had a very advantaged upbringing compared to Boole, and an advantaged life. Boole was happier. Boole was content. He lived a happy family life. He was very well balanced. So, but it's very interesting that these two giants and the two people who created new algebras were on this island. They did it on this island, and they had so little contact. It is fascinating, and I don't know. Is there any information out there that could shed more light on it? I know there are. There's a lot of Boole's papers available in the Royal Society, but I don't know how much, how if we'll ever get to the bottom of it. So yeah, and I think it's great that the work that UCC are doing, and I think that the demise of Grenville Place, the house, is I think it's symptomatic of our general attitude towards our science and maths heritage in this country, and I think it's something just while it comes to mind, it's something that we will be addressing in the Robert Boyle Summer School in June, Science and Irish Identity, and we'll be looking at various aspects that I think are relevant to this particular case, and we might try and look at Boole in that light there. Anyway.
Could I just ask, is there a plaque to the Boole Library in Cork, or there was plans to put a plaque up?
I think there is.
And there's one to Alicia, is there? Is it to Alicia Boole? One or not? Yeah, sorry, Conor.
Banners all around campus celebrating Boole.
Hmm.
And if you go on the walkabout on Saturday mornings, it's completely popular. I've been some events, like you do plenty. But George Boole appears twice on the walkabout in full Victorian garb and addresses the visitors.
I haven't been on it myself, but I hear wonderful reviews of it. I think it's
It's all been very enthusiastic.
yeah, the people, the devotees T's.
But the tour is generally different.
Hmm.
His bit is
Doing a bit.
mine was all accounts, and I had those banners about
Jackson?
Congratulations to you, Mr. Speaker, for summarising the importance of logic in engineering. In the early part of your talk this evening, you emphasised that the logic of engineering is very dependent on the natural logic. And I was very surprised to find in one of your marvellous summaries that one of the papers of Boole himself referred to the logic of science as being a science. I would have thought it was more dependent on being an art rather than a science. And only as your talk progressed did I realise what there is in terms of a connection between the science of logic and the art of logic. I also was, as your talk progressed, my mind switched from the early stages to the later stages, and therefore some of the thoughts that went through me have been overlooked. However, the the um, the family. First of all, when I saw the slide of the headstone to the grave of Boole in Cork, there was a huge blank underneath his name, which inferred to me at the time, it was an earlier slide than the offspring. And prompts me to ask, are there any of the families buried in or around Cork at this stage? And with regards to the logic, whether it be a science or an art, the thing I most remember about my own study of logic in the 1940s was the very dangerous question of asking somebody, have you stopped beating your wife yet? And that has always stuck in my mind ever since, one of the famous expressions. Thank you very much. It was a lovely talk. I enjoyed every moment of it. Thank you.
Right, thank you. I suppose, firstly, in terms of the science or the art, in the early 19th century, science had a different meaning to, and indeed art has a different meaning. But Boole would describe himself as a scientist, would talk about science interchangeably, you know. So whether, I mean, just like engineering, is engineering a science or an art? Of course, it's both. In terms of the Boole's family, Mary Boole was a widow with 5 children and needed to look for support for those, and she moved back to England, and she herself got a job connected with University College London. I think she was a librarian there. So the family moved. As regard, there could well be descendants of Boole living in Ireland. I don't know, but certainly if you believe in the genetic transfer of genius, his descendants have done remarkably well, made remarkable contributions in various areas, and that's a whole story in itself.
Such a remarkable amount of research you put into your speaker. Thank you.
You're welcome.
Elizabeth?
It's just perhaps a small follow-up to that, as to the position of logic vis-a-vis mathematics. There would be mathematicians who would see logic as the foundation in mathematics, and others who would see it as a small part of applied mathematics. Just again, perhaps shows the great variety that Owen has brought out for us in his talk.
Indeed, in one of my, in honour of Boole the other day, I had a Boolean puzzle in the journal.ie. One of the comments, this isn't mathematics, this is logic. This isn't a maths puzzle, this is logic. So that was one of the kinder comments, of course. But it that's interesting, and there's a whole story about how logic. I mean, Boole wasn't the first to look at applying mathematics to logic. There was Leibniz and others, and Leibniz, of course, created the binary system, which was another important strand. Logic passed into it became it passed into to the hands of pure mathematicians, but also then to philosophers. And interestingly, so mathematicians use logic, computer scientists use logic, philosophers use logic, and electronic engineers use Boolean logic. And there are at least 3 different kind of families of notation used, so that kind of gets confusing as well. So I was following more or less with my modern stuff, the stuff that Shannon adopted, and the stuff that pretty similar to what we use today in electronics. And I should say as well that, of course, Venn diagrams are another way of expressing it. So if Boole is expressing his logic in algebra, Venn diagrams express them visually. And Venn was, I think, a little bit younger than Boole. He was a contemporary of Boole's anyway. So that's another way of expressing
I
these.
feel another lecture coming on.
Oh,
But any other comment at the back?
I'm especially interested in when you refer to the way Boole enjoys the work of Aristotle and a number of other people, and I'm thinking of this when his dad held him to learn some languages, and he was left to all his things and said, I learned Latin, Greek, French, and German. So, and he also had access to the library, as mentioned. So in those days, that was only difficult. For a lot of the, did he depend on those languages to access the research work he done like Aristotle? Did they do something all into English? Did he use language that had been still the original?
Well, Aristotle would have been a standard text in English. It would have been a standard part of the kind of the educational canon of the day. But the others, the reading, he was able to read he was able to read the French mathematicians that were doing all the maths. As I said, in England, mathematics was kind of languishing in a kind of a dark age, and so his fluency in French was very important in that regard. And there are probably, we could speculate about the idea of learning several different languages, how that might have helped him see about the structure, might have helped him see about essence of language. So yeah, that could possibly be a factor.
Language itself as an object.
Yes, and he may have been able to see that speaking so many languages. So I think just to finish up, I'll apologise to people who maybe found the going through the Boole's logic a bit difficult and trying to read it as well. I hope I gave a flavour of it, but I do believe that no more than that we shouldn't talk about mathematicians or scientists or engineers without talking about their work. For me to come here and not show you Boolean algebra and just talk about Boole would be like coming here to talk about W.B. Yeats reading you a poem.
Well said. Can I just conclude then by offering our thanks to Owen for that presentation. Obviously, a fair amount of thought went into what he was going to say and how he was going to present it, and I think he did an excellent job. So please show your appreciation.